Hi everyone. People are still coming a little bit, so I'm expecting a few people to filter in as we start. But, are we recording already? Okay. Okay, I guess we'll start and we can recap things if a load of people come suddenly. So firstly, apologies for the layout of the room. It's not ideal for this. We have a fair few slides to show here. It's probably the best way of doing it, but that doesn't mean we don't want it to be interactive, so feel free to ask questions at any time as well.
One additional mic.
Yeah, we have a second microphone. So yeah, we'll get started. So there's three presenting today. Myself, Dan Handley. I'm the ARM Trusted Firmware Tech Lead at ARM, and we've got Inella and Vincent here, who will, I guess, will introduce themselves properly when they speak. So yes, it's a joint effort. So what we're going to talk about today is well, firstly, I'm going to talk about what is dynamic with an IQ at the end. For some people, this is a new thing, certainly not been talked about to Connect before, so try and disambiguate some of the terminology there. And then specifically, I'll go on to talk about what that means for ARM Trusted Firmware. And after that, I'll pass on to Vincent. We'll talk about the impact on OS power management technologies. And finally, Linaro will talk about a specific feature of dynamic that we're interested in, called L3 partial power down, which will become clearer later if you don't know what that means. Okay, so dynamic with an IQ at the end. You say it the same as the English word dynamic, but this is an ARM marketing term, and you see I've put the word TN at the end of that, to be ARM marketing compliant.
I thought it was dynamic.
Oh really? Okay. No, I haven't had a formal training for how you pronounce it. Yeah, it's a little bit confusing, especially to a lot of ARM people who've been working with this technology for a while, and maybe some of the people here who've had access to information before this became public. Then it was something known as flexible cluster microarchitecture, and so we're kind of talking about the same thing here. But if you look at the ARM website, which I pointed to here, the Dynamic talks about lots of different technologies. It's a very broad description. It talks about things beyond just what we intend to talk about today. So this includes things like architectural extensions for reliability, accessibility, serviceability. It talks about machine learning and artificial intelligence and stuff like this, and hardware interfaces for closely coupled accelerators. This is all very interesting, but not what we're going to talk about today. So I've kind of just highlighted the bits in green that we're getting on to. It's mainly around this kind of concept of big little within a single cluster, and also the specific power management interfaces and features, the latest architectures and platforms that we're trying to enable here. Microarchitecture, yes, not the architecture. Charles corrected me there, thank you.
I'm sorry.
No, it's fine. I'll just let a few people get a seat. So there's a few more here if people want. So yes, specifically we're talking about this part of Dynamic called the Dynamic Shared Unit, which is the marketing compliant version of flexible cluster microarchitecture. And so there is a public technical reference manual which I've linked to there, where you'll get lots more information than to present here about what it is. And there are many features, a lot to do with hardware integration, which are interesting, but not. I've kind of focused on, or we focused on the features that have specific impact on software. So, but there's more information there. If you want to get more information on DSU or Dynamic generally, I know that ARM's partner enablement group do training for this as well. So please go away and get more information there if you need to. But yeah, the features we care about is the DSU is specifically for the ARM v8.2 CPUs and later. So for example, the Cortex-A 55 and A75. And I guess the key thing about this is that you can have two different microarchitectures, up to two different microarchitectures within the same cluster. Beyond that, there's also flexibility to also have an L2 per core, although that may not be what happens in practice, but potentially you can have an L2 per core with a shared L3 crash across the cluster, whereas previous designs tend to have an L2 across the shared L2 across the cluster. And within this, there's also the possibility of being able to have asynchronous bridges to each of those CPUs, so you can plot them at different frequencies. Obviously, these kind of technology, the impact on the topology and how you lay out your cluster here has a big impact on the OS power management technologies, and that's what Vincent will talk about later. So I'm particularly interested in some of the hardware-assisted power management capabilities, and that's the bit I'll focus on, because that has the biggest impact on ARM trusted firmware. And as I mentioned before, there's another specific feature around this L3 cache that you can partially power down, and we'll talk about how the investigations that have happened so far with that and where we might be going in the future. Okay, so that's the basic summary of DSU. There is lots more information. I don't really have time to go into the very details of what the hardware provides there. So let's just talk about the ARM trusted firmware side. So regarding the hardware features, the power management hardware feature, the DSU enables these kind of simplified sequences for powering up and down the CPUs. Typically, prior to this, you have very specific sequences per CPU for how you power things up and down. And this is all kind of taken care of by the firmware, but it's a little bit painful and variable between microarchitectures. So this has been cleaned up, and it's much simpler for software. So there's less chance of programming mistakes and just less to do in software. So this is a good thing. Another aspect is this automatic coherency with the interconnect. Typically in multi-cluster systems, you have to do some programming whenever a new cluster comes on and offline to enable and disable coherency with that cluster. This has been cleaned up as well, so this is taken care of by the hardware if you set things up and it's integrated correctly. Another aspect is around the flushing of caches or general cache maintenance. A lot of the stuff that was needed to be done in software before you go into a low power state no longer needs to be done. Coherence is enabled throughout the power transition. I'll show that in a little more detail in the following slide. And finally, there's also this reduced power control communication, or the potential for it if you've got a power controller integrated into the platform using these hardware P channels, and you can effectively go into these low power states without even the power controller having to do anything. It's just the hardware takes care of it.
Good question. So the optimized coherency management, is that just for inside of the now larger cluster, or also if you have multiple clusters?
No, multiple clusters across the whole system.
Okay, so you have multiple clusters.
Even with multiple clusters,
got it.
yeah.
Thanks.
Yeah. So basically, just the firmware uses these new features now and enables an improved sequences for these powered down operations and power up operations using this new flag called hardware assisted coherency. This support is already upstream and available now. And so this improves performance for use cases like CPU idle, hot plug, and secondary CPU boot. But you have to enable it. It doesn't, it will still work without this flag. You'll just be doing a load of work you don't need to do. So people should be aware that you have to do something here. It won't just sort of fail if you don't enable it. So with this on, what we hope is that it will allow more aggressive OSDM tuning, so the latencies for going into these low power states will be reduced and coming out of them as well. So you'll be able to go into those low power states more aggressively. I can't prove that yet because there isn't any hardware to do that tuning on, but that is the hope. Although we're aware that people are going to have to be careful with the numbers they get out of the system. You may get some numbers that are seem quite impressive, but actually there's still stuff going on in the background after a wait for interrupt that the hardware's doing, preventing you from waking it up again. So that's going to have to be taken care of when you do that tuning. okay, a little bit more detail on this. I won't go into every single line in this slide, but this kind of shows the key operations that happen in ARM trusted firmware, at least in a CPU idle case. So on the left-hand side, the power down operations, on the right-hand side, the power up operations. And this is for ARM v8 8.0 CPUs. So when you send a PSCI CPU suspend call into the firmware, there's some validation that goes on. And for non-CPU levels, we have to take a lot because there is some shared data between all the different CPUs when you go into power states that affect the cluster or higher power levels. And then we have to do some coordination with some, in case those requests have to be downgraded, things like that. And then there's some CPU-specific operations like disabling the cache, flushing them, and taking the CPU out of coherency. And then there's some platform suspend operations, so that's where you communicate with the power controller typically to do the actual power down. And then we can release the locks and hit the wait for interrupt, and a short time later, hopefully, everything goes up. Similarly, on the way back up, we have to do some minimal control register initialization to make sure we're in the right state before we do anything really, like setting the engineers. And then there might be some platform-specific reset handling. Hopefully not, but some platforms that maybe have some errata or some problems. They have to do something very early on before you can do anything. And then we do some CPU-specific reset handling, things like errata workarounds for the CPU, and then entering coherency for that CPU. We enable the memory management unit. Unfortunately, we can't typically enable the data cache at the same time as enabling the memory management unit at this point, because on ARM v8.0 CPUs, if you've got multiple clusters, that you have coherency across all the clusters. So we have to leave the data cache off for a little while until these platform suspend finish operations that they're called, where you enter coherency for that cluster. Then we can enable the data cache and restore the OS context and do any things like updating statistics and return to the operating system. So that's the general flow. For v8.2, it looks like this. Now, it might be not very easy to see what the difference was, but I'm going to point that out, so don't worry. So there are a few things that changed when I went between those two slides. One is that on the left-hand side, the D cache is enabled all the way through, right down to the wait for interrupt, so we don't need to disable it at all. So all those operations after them should run a lot quicker. And similarly, on the way up, we can enable the D cache at the same time as the LMU. Now, because the coherency is maintained across the whole system. Other things that are improved, we don't need to do those explicit cache flushes anymore. And, or at least that maintenance that happens after the cache is disabled. So that's a good thing. The other one is around the actual locks themselves. Important characteristics, because we don't have coherency across the system on the 8.0 CPUs, when we require locks, we can't use simple spin locks because they're not guaranteed to be applied across the whole system. So we have to use these software bakery locks, which are very slow. So now we can use spin locks, what is one advantage, but also another feature in v8.1 was the addition of this compare and swap instruction, which means spin locks are also more efficient, so we kind of get a double bonus there. We hope, although we haven't obviously measured that, what the benefit is. And finally, it's around these platform operations. They should be much reduced, hopefully reduced platform power controller communication, and hopefully less internet programming. But this all depends on the hardware design as well. You've got a power controller and the firmware along with that supports all this. So finally, where we're going with this, so there's a little bit more we can do around. There's this cluster voting register, which effectively you can vote per CPU whether the cluster should go down for certain operations, which means that if you're the last man in this last CPU in a cluster to go down, the hardware, and all the other CPUs are voted to go down as well, the hardware will just go into turn the cluster off as well as the CPU without any communication at all with the power controller. There's some work for us to do to enable that. We need some support from the power control firmware to enable that. And with that as well, we should be able to either remove the cluster level locks, because there'll be less shared data required between CPUs, or at least reduce the time they're held. We're not quite sure about how the statistics support will work there, so we might need to still have some kind of locking there to be determined. And finally, we just need to actually analyse this on real platforms and see how much we get and if there's anything more we can do. Yeah. So that was my part. I hope I'm not using too much time. Yeah. I'm going to pass on to Vincent, unless there are any questions right now on that part. Hi.
I have a question there.
Yeah.
So if you don't use the battery locking, so change to the spin lock. So that means that the inclusive monitor should be work on the L3 cache, or not, because if you don't have the L3 cache, then that means the inclusive monitor should be work on some hardware logic. So I just want to confirm that if you use the spin lock, that means the L3 cache should be enabled, right?
Your coherency fabric is involved. You might have.
I'll let Charles answer.
You might have configured a really like a zero-size L3 cache. The coherency is working. That's what it means. The fact that the L3 is one way of implementing that is just kind of irrelevant.
But the first CPU, when the first CPU put up, then maybe L3 is by default enabled or not.
Oh yeah, the whole cluster has to be enabled, and the logic within it has to be enabled for the CPU to run it. Yeah.
Any more? No. You can ask more at the end anyway.
All the code is upstream.
Sorry. Yes? Yes, all the code apart from this future stuff I mentioned here is upstream. Yeah.
It's
The hardware assisted coherency flag.
The ATF 1.3 or?
Yeah, the latest release is 1.4, but I think it was before that. Sometime between 1.3 and 1.4 that it was upstream. So just if you want to look at the code, just do a search on that flag, HW assisted coherency, and you'll see all the changes. I'm conscious of time, I want everyone to get through their bit.
Hello. So I'm going to speak a bit about the support of DynamIQ in the OS and more specifically in the kernel. So for DynamIQ, ARM and the PMW team are going to collaborate on enabling that. So that's why I'm presenting that. But the work will be done by both PMW and ARM Cortex-A. So this is an overview about what will be supported and which kind of change we will have to do in order to make the full support. So this is an overview of the DynamIQ and all the PM features that are enabled. So compared to the big little system, we have a finite range power capabilities with per CPU voltage, per CPU domain, and per CPU power domain, and per CPU clock domain. So in fact, we can have a really fine-grained configuration from both frequency and voltage domain. We can have also per DSU frequency and voltage domain. So the support of that in the current kernel PM framework is already there. In fact, I mean, there is nothing new from a kernel point of view to support per CPU frequency domain, per CPU voltage. Intel are already doing that. So, I mean, we already have PM domain, we already have CPU flex, CPU idle that support that without any change. Maybe we'll have some change, I mean, we'll have some few change, but nothing really significant on that part. We can already describe all this topology quite easily with the kernel, with the power domain, with everything. So we don't expect any major change on that. Then from a scheduler point of view, so this is in the current implementation. So we have big little systems which are described using the scheduler topology. And with the current big little system, in fact, all the domain are congruent. I mean, all the frequency domain, cache domain, power domain, voltage domain, and the physical cluster are all at the same level. So we have one frequency domain per cluster, we have one microarchitecture per cluster. The last level of cache is the cluster, so everything is fine. So what's happened right now, so this is an example of a 4-bit core and 4-little core architecture, and how the scheduling topology is described. So we have a first level where, so this is the point of view of the bit core. So we have a first level, which is what we call the cluster level, in which we describe all the bit core, and on which we can attach some energy model describing the power capabilities of each core. And then we have the die level, where we can see the host cluster, and for which we can also associate typical dedicated power domain. So that's the current implementation, and we can see that the frequency domain is there. So we can easily match the same energy model, the same for the voltage domain, and also from a CPU idle point of view, everything is aligned with this current topology. So with DynamIQ, and the fact that we can have several microarchitecture, for example, in the same cluster, that we can have different physical, we can have different clock domain, different power domain and voltage domain. We can have a difference between the scheduler topology and the power topology. So this is the example from a scheduler point of view of the topology. So we have this last level of cache, which is the cluster level, where we can see all the CPU, big and little. And this doesn't match anymore with what can be the power domain, the frequency domain. So we can't easily put any energy model for each level. So that's why we need some change in the scheduler topology, where we can put back some energy model level corresponding to each power domain. So in order to do that, the goal is to introduce some phantom domain. By phantom domain, it just means that it's not a real scheduler domain, because that doesn't give any benefit from a scheduler point of view, but that enables to describe the other topology, the frequency topology, for example, or the physical topology. So in this case, for example, we still have this cluster, this last level of cache domain that is available, and we also describe a new level, physical cluster level, where you can add some power model for the cluster impact. So that's the main difference. The main difference is really, yes, creating this new domain, which doesn't create any new scheduling logic, but more some power consumption estimation computation. So in this example, I'm back. So in this example, we have the 4-bit core, which are sharing the same frequency domain, which can be quite similar to what we have right now with the big little. So in this case, we are creating this phantom domain, where we can show in the topology that the 4-bit core will share the same frequency, so changing the frequency of one CPU will impact the other one. They are sharing the same power, capability. So that will be the main first change that we will apply in the kernel in order to support the DynamIQ. So that will enable us to reuse the current ES algorithm and all the power domain stuff that we have in place. But that's the beginning. And after that, our goal is to improve and enhance the support of DynamIQ with more changes, like the fact that we can share some frequency and voltage domain between CPU and the DSU, for example. So this will have an impact, and our goal will be to study that and how to integrate that in the current scheduler. And also how to propagate any change of one device to another one because of shared voltage domain, for example, or shared frequency domain. And the last point also is the support of multiple DynamIQ clusters, which will be also part of the list. Yeah.
I was just going to say that the sharing problem is real already today. You don't need dynamic to have the sharing problem.
Yeah.
It's just worth pointing out that the work's more
No,
generic because of that.
The point is that actually everything was, the topology was the same, so it was easier in that sense. Now we can have some different topologies, so we can't only rely on the scheduler topology to propagate. But I agree that it's already the case. We already, in fact, right now we have a DynamIQ where we have per microarchitecture frequency domain and voltage domain, and that. So that's what we are going to work on the next 6 months. And our goal is to provide some this phantom domain and start to work on supporting more enhanced activity. Have you got any additional questions?
So what do we mean by the shared frequency domain here? Like the big cluster and the small cluster will change the frequency together?
For example?
Repeat question.
More likely, sorry.
But they will have different powers at the same frequency, right?
So you already have today. You already today see big little systems where they've gone and shared the volume thing. I mean,
right.
that's irrelevant on dynamic or not, right?
Right, but
I'm
I'm
just trying to make. To me, this work is more generic than just about dynamic. But in dynamic, the interesting thing about dynamic is that it opens up the possibility of having anything from per core DVFS to per group of cores DVFS. And so it opens up the possibilities of a variety of topologies, right?
I mean,
and so that this making the point that
dynamic actually gives you that you have different clusters.
So we need to.
Yeah.
I think what dynamic does is it gives you like different microarchitecture in one physical domain, which is our classical cluster. That's specific dynamic. But when it comes to frequency domains, power domains not being congruent to the physical layout, that's some problem we have in other architectures as well.
Yeah. So the point will be to study more the impact of sharing a voltage domain between different parts.
Exactly. Can I make a comment? It's sort of also a natural progression of Big Little, right? When Big Little first started, it was a premium end feature, right? So any traditional Big Little system would have had voltage frequency domain for a big cluster and another one for a cluster, because it was a premium feature, right? But what's been happening is that Big Little's become pervasive, right? And people want to have that marketing tech on medium range and low range, and then they have to start to make saving decisions. One of them being the moving voltage domains, right? So even on existing silicon today, dynamic just opens up more possibilities, but essentially, even existing silicon today, you will have systems that claim to be Big Little, but actually when you get down to the nitty-gritty, they don't necessarily have a separate voltage to make Big Little. Right? So this is about studying. This is a perfectly logical progression for EAS to move into figuring out how to deal with this going forward, because we see more and more of these in the market, and we'll see the same with dynamic.
A question from my side. How far you want to go? I mean, it's all about like traditional systems are all symmetric, right? And the scheduler code can handle symmetric systems very well. The problem always starts when we introduce some kind of asymmetry in those things. Do you already have a feeling how far you want to go with the support of those asymmetric features? Like the frequency domains, power domains, physical layouts, microarchitectural domains not being congruent? I mean, if the number of cores and clusters actually goes up, then there are more and more possibilities to create more asymmetric features into the system. And it's not really clear to me how far we want to go with this, with the next step support.
For the next step, that's the next step. We don't have any definition. It's just that we know that we'll have to move more on this activity. Right now, the goal is really to have the basic support with this quantum domain that provide you something quite similar to what we have with the Big Little right now. And then we know that the shared voltage domain can generate some additional issue that we'll have to fix. But yeah, that's something we haven't started to work on. That's the next. Any more questions? Yanela?
Hello. My name is Yanela. I'm part of the ARM Power Management team, and I will take you to the last set of slides that have to do with L3 partial power down. And one important thing that you have to remember in regards to dynamic is the fact that it offers finer grained power control in order to improve efficiency, energy efficiency. And this doesn't only apply to cores and group of cores in those frequency and voltage domains or performance domains that Vincent was talking about. It also applies to the L3 cache. And the L3 cache is part of the TSU. You have to imagine it as having an implementation-specific number of portions. And for the first revision of the TSU, that number is 4. So we can split our cache into 4 portions. And what will happen is whenever you need additional performance, you will increment the number of portions. You will power on additional portions to have a higher capacity of the cache. So we're talking this in terms of capacity and not frequency. So we're increasing the number of portions to have a higher capacity, and whenever we're not using that capacity, we're powering it off in order to save energy. I'm going to take you through the software, the support we have in software for this functionality, and it's an out-of-tree implementation at the moment that is hosted by Linaro. I am going to skip to the architecture slide that basically gives you a visual on how the design of this is, and this is in the form of a DevFreak driver, which brings you both the decision-making process of upsizing and downsizing your cache and powering up and down your portions, and that's part of the DevFreak governor. It uses hit and miss counters in order to make that decision, and that decision is then passed to the DevFreak device that writes a control register and sends that information to the hardware to implement. And as Dan said, there is no need for cache management operations in software. So the hardware will do that automatically in order to maintain coherency. Whenever you are powering off a portion of your cache, it will also take care of cache flushing and all the operations that are necessary in order to maintain coherency. The design of this was done as to have a bias for performance, because it's always better to have a cache enabled in order to improve latencies. So we always consider upsizing our cache, making our cache have a higher capacity. We consider it more often than we consider downsizing. So we're trying to keep our cache at a higher capacity for a longer amount of time. And that's done the moment at the 10 millisecond stick. So the 10 millisecond stick, we evaluate the need to upsize our cache. And 10 times slower than that, at 100 millisecond stick, we're going to consider the need for downsizing. The next slides are here to take you to the decision-making process of upsizing and downsizing the cache. How do we know if there's a need to upsize our cache? And basically, we know this based on the use of the cache. We're trying to balance the need for a higher capacity cache. We're trying to balance the need for higher capacity cache with the energy efficiency of having a large number of portions enabled. And the condition there that's implemented in the governor at the moment basically translates to is my missed bandwidth, that is my number of misses in the last 10 millisecond interval, as high as to justify my cache having a higher capacity cache, enabling another portion in my cache. So, in terms of energy efficiency, if you see the formula for CV as being the leakage for one portion over the energy for going to the dynamic energy for going to DRAM, we're basically, in terms of energy, we're balancing the expenditure in energy in powering up a portion that's sort of increasing the static leakage by the savings we get in DRAM dynamic energy by not having those accesses, those misses, go to DRAM. In terms of bias and performance, we have part of the equation there is the TU, the upsizing threshold. And basically that tells us what part of the energy of one portion of the cache we're willing to ignore when making the decision. Basically, we're trying to favor performance. We're trying to increase the number of portions of our cache without actually the need for higher capacity cache to cover the entire cost of it. And if we take the extremes for the values for TU, for example, if that is 1, we're basically comparing our miss bandwidth with 0. So for whatever small number of misses, we're going to decide to increase by 1 portion. The other extreme is having that value to 0. So basically, we're trying to justify the entire portion, the energy of the entire portion, whenever we're deciding to upsize. The reference implementation we have now has considered that value as being 0.9. So we're basically ignoring the energy that 90% of a portion consumes when making this decision in order to enable performance. The algorithm for downsize is similar, but here we're balancing the use of our higher capacity cache by the energy efficiency of having that higher capacity cache, by having n, which is the current number of portions enabled. So in terms of energy as before, we're balancing the savings we get from downsizing our cache, from reducing the number of portions, by the expenditure in DRAM dynamic energy that will come to happen if those hits turned into misses. So basically, we're evaluating the number of hits as our information in regards to how well the cache is being used. And as before, we have the TD value, the downsize threshold, which establishes that bias for performance in terms of how much of the energy leakage of one portion do we want to ignore when making the decision in order to keep a number of portions higher to have better performance. So this gives you a bit of a visual in regards to how the algorithm works, and this has been obtained by running a memcopy of 4MB on a very simple system using one of our internal models. And it's a 1 CPU system with a 2 MB L3 cache. And the smaller plot here, I made it specifically small because the only things we need to see here is the behavior during that 4 MB workload. So basically, before running the workload, we have a 1 portion enabled, so the minimum number of portions enabled. During the workload, we have to increase the number of portions enabled so we're getting to the full size of the cache. And after the workload, that's being downsized back to 1. The plot on the right is more interesting because it shows you why those decisions were made like that. And what we see before the memcopy workload running, we see that first of all, what we have here is we are representing both sides of those conditions we've seen before in the upsizing and downsizing decisions. We're representing, first of all, the hit and miss bandwidth by those red and yellow crosses, and we're representing the miss and hit thresholds by the blue and the green lines. So the way that the decision is being made, for example, before us running the workload, we're seeing that the miss bandwidth and the hit bandwidth are very low, are below the threshold, so there's no need for a higher capacity cache. When those values get over the threshold, we will have a continuous request for higher capacity cache because there is a lot of traffic being generated. As you see, during the workload, it's being maintained at a high level, but we cannot give it more than the full capacity of the cache we have it now, and it will maintain up to that level. After the memcopy workload is finished, we'll see the mid bandwidth, the hit and miss bandwidth dropping back to low values, and the upsize decision will not hold. So when checking for the downside decision, we'll see that we don't need such high capacity cache, and we end up going back to 1 portion. So we're comparing the values for miss and hit bandwidth with those thresholds. And one thing to see is the fact that the miss threshold, which is the blue line, it's a constant. So it basically says that it shows you the threshold that you need to justify to increase 1 portion. So it's only representative for 1 portion. When you look at the hit threshold, you see that that varies with the number of portions. So being below that, it says that you don't have the number of hits as to justify having that number of portions enabled. This shows you more of a generic behavior, how it should be, and what we should be seeing here. So we've run a number of workloads, CPU-intensive workloads and memory-intensive workloads. on a number of systems, or with the same system with different L3 cache sizes, varying from 512 KB, 1, 2, 4, and 8 MBs. And in order to see how to actually validate that the behavior is proper. And what we should see here, and we are seeing here, is that for CPU-intensive workloads, this should not affect, it should not raise the number of portions, as there is not enough traffic. And for I/O-intensive workloads, we should see an increase in the number of portions, only depending on how well used the cache is. So for DriveStore, for example, we're seeing the number of portions always stay at 1. The same thing happens for a memcopy fitting into L1 and L2s. And for DRAM, for memcopies that hit DRAM, for example, 16 MBs, it will stay at a full number of portions all the time because it has high traffic. For the interesting behavior is the one for DL3, as we're seeing that by maintaining the same memcopy, the same buffer for the memcopy workload, and I've used a 512 KB memcopy workload in this system. We're seeing that as the cache gets higher, we need less and less of its capacity in order to handle that workload. So things that you should keep in mind in regards to this initial reference implementation is the fact that the portion at the moment is considered as being the smallest unit that can be powered up and down. And when we're making when making upsize and downsize decisions, so from hardware point of view, that might not always result in proportional energy consumption or energy savings. So and the algorithm relies on the fact at the moment that when you're increasing your number of portions by 1 or decreasing the number of portions by 1, you're basically saving the proportional energy, 1/4, 20% of energy. The advantage that the algorithm has for this situation is that it can handle logical portioning as well, so you can group together a number of portions that will result in that behavior and have that passed to the driver. At the moment, there is only support for a single dynamic shared unit, and the way that it is now, it's not suitable for use with a simple on-demand governor. And as you've seen, we've implemented our own sort of on-demand governor that has 2 metrics when it decides to modify the performance of the cache, when it decides to upsize and downsize. So the simple on-demand governor basically has 1 metric, and that would have to be fed into that behavior. On investigation we are having the moment is the possibility, we're investigating the possibility of moving this functionality into the ARM trusted firmware. So as you've seen, the current functionality does not tie it in any way to the kernel, it doesn't tie it to the OS, it's basically using some hit and miss registers, passing them through an algorithm, and writes a control register in order to pass that information to the hardware, so it doesn't use any of the OS framework. So it could as well fit into ARM trusted firmware, and we're looking into piggybacking on PSCI calls in order to give us that tick of analysis for us to decide when to upsize and downsize the cache. And of course, we have to look if those calls are often enough as to maintain a proper analysis. For more details on this, you can look over the reference document, and the same thing for the elements that Vincent presented. So thank you very much for listening, and if there are any questions.
It was after lunch.
This is the power down and power up. The DVFS or the L3.
Okay, so this does not manage frequency. This only manages the capacity of the cache. So it doesn't have to do with any voltage or frequency changes. It only manages how much of the cache you're keeping powered on.
Effectively changing the number of ways in the cache.
I know. Do you have the plan to develop a DVFS governor?
Not at the moment, no. So I'm not aware about the roadmap of I don't know, other teams, but I'm not aware.
It would be difficult for us because it would also be part of that silicon vendor's strategy for performance management of other elements of memory as well. So I don't know that it would be appropriate.
Okay.
Thank you.
yeah, any questions on in parts of it, or any comments or thoughts, things we should be doing differently, or what I was saying good?
Yeah. Just follow up another question that before, if we use the software method to flash the cache, so we can easily to get to low the latency for the CPU idle entry and exit. But now, if we use the hardware method to flash the cache, so how we can get to know the real latency?
That's a good point. I would hope in the future when we start to see these real platforms, maybe there'll be some hardware counters or some other measure that we can find out what's going on and inquire, after the fact what went on. But I think in early implementations that might be quite difficult to determine. Maybe you could sort of infer it by, trying to hit the power controller to power it on, and if it didn't respond, then you know it's still doing some stuff, and you could try to work out what that latency is. But I think we really need to see some hardware to see if that would work.
Can you see that with the power consumption of the power domain?
Possibly, if it's responsive enough, we could measure that. You've got good enough tact on the hardware. Yeah, possibly.
Like as you said at the beginning, when you first start measuring on.
Sorry.
As you said at the beginning, when you first start measuring on real hardware, we're going to see numbers that are phenomenal.
Yeah.
But there's a lot of things that are being pushed back to the hardware that, like Leo said, that we won't be able to measure to start with. So in my opinion, that's a real, it's not misleading, but it's something that needs to be addressed in order to really understand what the system is doing, how the software can do better things.
Yeah. I think you're right, because there's going to be some things we can't measure, but
I wouldn't like to lose the message that ultimately this is all upside, right? We're getting much simpler software for starters. The CPUs also would now all have basically all of the 8.2 CPUs rather have the same methodology for turning on and off, rather than a different one for each TRM for each CPU. And you'll have enabled heterogeneous and caching way earlier than by later in the shutdown and way earlier than
I salute the hardware support, but we really have to have the means to understand how long that hardware support is costing us, or how much it is costing us.
With the 8.4 activity monitors that might help here potentially. I don't know in the future.
Yeah, maybe actually, because you do have things like construction return and stuff like that. So maybe.
Yeah. So future architecture 8.4 onwards has potential support. Yeah, it's not hardware specific, implementation specific counters for this time.
From the scheduling latency point of view, we mostly care about exit latency, which we still could, which this model also gives you the accurate result, right? Because you ping CPU to exit, and when it exactly exits, you can take the diff, right? So exit latencies will still be accurate. Only the idle entering is the only one that would be right. Exit latency.
Correct. Yes, unless the power control firmware is kind of lying to you a little bit. No, I suppose you could still. Yeah, no, you're right. Yeah, you could still, if the power controller didn't respond to the exit, then you could measure that. Yes. So yes, you're right.
So what I meant to say, right? For example, if a task is woken up on a CPU2, which is in idle for class.
Sorry.
What I'm saying is that, right? Say for example, you actually woke up a task on CPU2. Say CPU2 is an idle.
Yeah.
So that's where you note down the timestamp where exactly you woken up a task on the CPU2. That is your idle exit starting point. The moment that CPU2 actually comes back to OS, right, and executes the first instruction where you put a trace point, the difference is the total time the CPU2 actually took to exit idle.
Yeah,
so that number still be accurate for this model also.
Absolutely, yes.
Which we mostly care about.
Well, DVFS we also care about.
Yes, but CPU idle enter, you don't care much, right? It's just more like a.
You care if you're trying to turn on them very shortly afterwards.
Yeah.
Yeah,
yes.
the last,
We care of the last atomic intersleep.
Yes.
When you send the final command and you can't stop until going down and then going up. That's what we care, and that's where the this uncertainty is easy, because you will have to finish the maintenance before going it.
Okay.
Is there any other question? Yeah.
One other thing, so on x86 we typically have those turbo states that are completely managed by hardware. So if as long as you're in the highest frequency state, then the operating system doesn't even see you going into additional voltage and frequency states that give additional performance. Are there any plans to do the same as well? Yeah.
Everything in this case is started by hardware.
Okay, so the hardware could do it within the current model? Or?
Yeah, but in fact already now we can do that. I mean, as long as your hardware is able to increase, to manage both your clock and your voltage simultaneously, we can have an hardware that automatically increases.
Right, so as far as the OS is concerned, that would just be one power state that we enter and then...
Yeah.
Okay, got it. Yeah.
Wrap up?
Yeah, just one last thing. So we usually have some 4-10 hacking session on the afternoon. So we'll have one around DynamIQ tomorrow afternoon at 2 p.m. I don't remember the room, but it's on the full schedule. If you want to discuss more or less important.